Okay, let's start. Do you have any question? All right. So last time we were discussing some roughly this 2.1, 2.2, the idea of a linear system, okay, of first order ODEs. Okay, so the format, the generic format that we would consider is something like this. Let's say y dy, okay, over dt is a function, right, as a vector function of t and y, okay, where y, vector y, right, is going to be y1 of t. So far, you only see two coordinates, right? But there's no reason why it has to stop there. The discussion that we talk about here kind of, except when we graph, applies to n-dimensional, all right, vector, okay? So it's just a vector of, it's a vector field, right? It's a vector of n dimension. And f, right, is also a function that takes in a time variable and a vector variable, right, and output a vector, because this is the derivative. What else do we want? This can be given an initial condition, right? An initial value problem. Okay, if the value of y at 0 is given. All right. So what kind of concepts that we kind of discussed last time, right? So several concepts. Right. The first is the idea of models, right? So we talk about two models. One model is the predator-prey model, right? Predator-prey, where you have the RDT is equal to R times 2 minus 1.2 F, for example, and then the FDT is F times minus 1 plus 0.9 R. Okay. And so here, right, of course, the question is, right, why F is predator, R prey, right? In this question also, right, the equilibria, okay? Meaning how, what kind of population, right? What kind of population distribution of R and F that if we start there, we'll stay there. And then there's also the idea of the solution curve, okay? Basically, the graph of SketchUp, right? Let's say F versus R, right? As a graph. Okay, so we will go back to this a little bit later, but these are things that we considered last time. The second model, right, is the spring mass system. Where for now, right, all we're looking at is something like, what was it? So we have a spring, right? And then attached to a mass, where what we call by y of t is the position, right, away from equilibrium, right, position of the mass at time t. And of course, right, y equal to 0, right, is equilibrium. Okay, so this is a spring like this. All right. And the equation, right, for the position of y is that you start out with F equals to ma. F being the spring force, right, is in the opposite direction of y, right? And then it's going to be my double prime, or you get my double prime, right, plus ky is equal to 0. Okay, for now. So the question that we consider, right, and the main question was how to convert this system, sorry, not the system, right, this equation, this second order linear equation into a system of first order, right, ODEs. Okay, so first of all, right, it's second order because the derivative on y is the second derivative. It's linear, right, exactly the same as when we discussed the first order equation. All the powers on y and y double prime are 1, right, and the only combination between them is plus minus, right. Of course, there's like a more rigorous definition, but roughly, right, the structure is linear here. Yes, and actually the question in general is this, right, or how to do, right, how to do this in general for now, right. Let me just quote a second order equation, but it can be a high order equation too. Let's say a double y double prime plus by prime plus cy is equal to, let's say, let me call this f of t, all right. I'm still on, right? For some reason, something get flashed and some people disappear. You still hear me, right? Okay, thanks. All right, so basically, right, what's the difference here? Here, you only look at the spring force. There could be a drag, okay? There could be like a viscosity force when you dip, let's say, the spring into like, a solution or something, all right? So there will be a drag term that's proportional to velocity. There could be an external force acting on the spring, acting on the mass, right, besides the spring, okay? But anyway, from our point of view, right, this is like a general second order linear equation with non-homogeneous right-hand side, right? This is a homogeneous equation. So that's the kind of question we're concerned here. Of course, like after we pose it, right? After we pose into a system, right? After we pose into a system, then whatever questions we asked from before, like equilibria, solution curve, sketch, will also be applied, right? But in terms of the spring mass system, the more of a the point, or not the point, but like the difference, right, or the new thing is how to convert a higher order linear equation into a system of first order, all right? And again, the gain, right, is that you reduce the order of the equation. You reduce it from second order to first order, or actually you can do it for like higher order as well, like fifth order, you can reduce it down to 5, okay, first order equations. Of course, the loss rate is you have to convert to a system, but so the gain in general is that we just have to look at everything as a system, okay, as a system. And then we can just, whatever we say about system works for other equations too, like this. So the steps here, right, is simple. you start at y, right? And let's call that, I don't know, right? Let me switch variable here. You call that the first coordinate, okay? So that's the first coordinate. Just let that be y. And then the second coordinate, right, will be y prime. Or rather, right, let me do dy dt if you want. Okay. And that's enough. Why? Because the next one will be a derivative of this of the second coordinate, right? So after this, then you're good. Because then you convert the equation, right? You convert the equation to a x2 prime, right? By prime we mean dx dt plus b x2 plus c x1 is equal to f of t. Okay. And then so the system will be right here. So here, right, of course, dy dt is x1 prime, right? So the system will be x1 prime is equal to x2. x2 prime is equal to, well, you just convert everything on the left-hand side onto the right-hand side. So you got, let's see, right, minus, right, minus cx1 minus bx2, right? And then I guess everything divided by a, right? And then plus f of t, like that. Okay. And notice, right, is exactly in the structure, right, of a vector, right? A vector derivative is equal to a function of that vector, like that. Okay. So that's the conversion. You can convert any high order equation, right, into a system with this approach. So now we'll go into more details, right, into equilibrium, solution curve, sketch, that kind of thing. But any question before we continue? All right. So equilibria, right? So let's go with the abstract formulation. The abstract formulation is dy dt is a function, right? A vector function of fty. Yeah, because, right, again, the point is what? The point is to transform this into a first order equation. If you only have one variable, then essentially you're just talking about y. But this equation involves the second derivative of y. So there's no way you can reduce that down to a first order, right? So the trick, right, exactly the trick here is what? You give the second variable as the derivative of the first one, so that the second derivative, right, the second derivative term is exactly the derivative of the second one. Okay, that's how you reduce a high order into a single order, first order. Yeah. So, all right. So the equilibria, right, are the points. So y0, right, or whatever. So a particular point, right, a particular vector y0, right, is an equilibrium, right? Oh, sorry, right, forgot. So first of all, equilibrium, right, as a concept only applies to this kind of function. All right. So Carl, like if you were to take 244, then I would spend like, I don't know, like a whole chapter teaching you how to solve this in this form, actually, which we'll talk about a little bit, you know, and we will discuss all the fun thing about, you know, variation of parameters, undetermined coefficients, that kind of stuff. The point of view of this book, though, right, on 252, somehow is they would like to not discuss this explicitly, but transform it and kind of put all the weight onto the system. And that's why we transform it to first order, to a system of first order, all right? Not just a single first order, to a system of first order. So the message is that you don't need to learn too many methods. You just need to learn the method on how to deal with the system. Then you can handle any other higher order equation by transformation. It's up to you, right, to see whether it's efficient or not. But I'm following the textbook, so that's the philosophy. The other textbook, right, the other class, kind of appreciate both approaches. They show you both. So yeah, but I'll mention this approach too. Yeah, all right, very soon today too. Yeah. So yeah, one thing I forgot, right, is that there is the idea of, right, autonomous equation, right, which is exactly the same as, you know, the one-dimensional case, right? That an autonomous equation is when the right-hand side does not depend on t, right? So the evolution, right, the dynamic never changes with time. So equilibrium and stuff like that, right, only makes sense in autonomous system to begin with. So why not is an equilibrium, right, if, right, f of y0, right, is equal to a zero vector, all right, because it's zero everywhere, okay? Because that means that the derivative, right, the change in time is not, right? So of course, example is, let's say something like this, right? And dy1 dt, let's say is, right, y1, y2 plus 1, right? And dy2 over dt is, let's say, right, y1 minus 1 times y2 plus 4, okay? Something like that. So of course, right, you know, roughly the idea is you just search for every combination, right, that makes the right-hand side equal to 0. Except remember, we observed, right, last time that it looks like there's 4 pairs, right, 2 by 2, so 4 pairs, but not all pairs work, all right? So we just have to pay attention to that. So the idea is, right, we just kind of match. So, right, so here by listing out, I mean the point y1, y2, right, which is a vector y, right? You just list out the value that makes the top 0 and search the bottom to see what could correspond to it, right? So if y1 is equal to 0, right, the tops is 0, this is minus 1, so this must be minus 4. Y2 can be minus 1, right? That will make the top 0. And then, right, that would be not 0 here, so that must be a 1. But you see that, right, that those are the only 2 points, right? All the combinations will not make both equal to 0. Okay, so again, I'm not sure someone asked last time, right? You must make both 0, right? It's a 0 vector, not a 0 point. Yeah, which Laura, Lauren, about the way to do it? So yeah, right. You go from top to bottom, kind of, right? You search the top. No, because you will get the same thing. From bottom to top, you get the same thing. You see, because basically, you see, for example, here is 1. Then you search the top, exactly, you get minus 1. Right? And you search minus 4, you get the top to be 0. You just have to do it once. Lauren, I'm not sure what point you want me to repeat, but yeah, basically, right, you go from top to bottom, you fix, right, and you find the value, right, one coordinate to make it equal to 0, let's say. Now, if you fix that, okay, you fix it. That means that you already have the top equal to 0. Correct, I plug in 0 for the bottom because the top is already 0. Right, by my choice. So you see what I mean? First you do this, 0, comma, question mark. And then you plug in 0 here, you see exactly the question mark will be 0 minus 4. And then you repeat, right, for the second factor. you got question mark -1, and then you go to the bottom. You see that -1 here, so that must be a 1. So the question mark will be 1 minus 1. Is that okay? So I'll let you think about that a little bit, okay? How did I get -1? Because I set the top equal to 0, right? I set the top equal to 0. All right. So maybe, right, steps like this, right? Steps. Set, right, top equation to be 0, okay? Pick out the factors, okay? For each factor, you get a sum, okay? Fixed values of y1, y2, or something like that. All right. You plug those into the second equation, solve for the corresponding remaining coordinates in the second equation by setting it equal to 0. All right, so that's a steps. Yeah. All right, so that's that, right? And then you just repeat. I mean, you see it. All right, just take some practice. So that's equilibrium. That's how you find it. All right, that's how you find it. But of course, question for the future. All right, question for the future, not now. You know what's coming? Classification of equilibria. All right, you see it. I think in chapter 3. Yep, because again, like Lauren, what happens is when I plug this into here, right, I will get both of them to be equal to 0. What does that mean? That means at this point, basically, if you start out here, then the y1 will not change, y2 will not change. That means it's on equilibrium, right? Same goes for this. So I might have switched kind of freely, right, between coordinate notation and vector notation, but you know, they're kind of the same. All right, yeah. So we will have classifications of equilibria, right? Like the one-dimensional case. Source and sink will make a comeback, but you will have also something like, I think, God, what is it, a center or something like that, right? And I'm not sure if there's another one, but basically, right, we don't have enough tools now to do this, but that will be a future question. Of course, along with this question, right, will be something like long-term behavior, right, of solution. Right, basically asymptotics, right? So as time goes on, right, as time goes to infinity, does it go to the equilibrium? Does it go away from the equilibrium? Does it circle around the equilibrium, right? Same exact kind of question too, but done on a higher dimensional, right, context, all right? But so that's equilibrium for you. for now, right, what we're gonna play around with is the second concept called solution curve. And vector field. Okay, so we will play around with this for a little bit. So I kind of talked about it last time, right? For example, the predator-prey system. Okay, where you have, let's say the RDT is 2 minus 1.2 F times R. The FDT is equal to minus 1 plus 0.9 R times F, right? Yeah, this is 2.1, 2.2. So the solution curve, right, will be basically the graph of one variable versus the other, right? This is a solution curve. And on the solution curve, right, you have, basically you mark out equilibria, right? I mean something here, for example, right? And then, of course, at equilibrium, you get there, you stay there. A mix, all right. I'm kind of free flowing between 2.1, 2.2, because I don't see the point of, you know, like really just doing one section at a time. These really kind of are connected. But yeah, I mean, both. And then, but then if you start out somewhere else, right, then the textbook kind of says something like this. It's like a, not a circle, right, but something like that. And let me just do one more, right, something like this. Okay, so what do this mean? This is like, you know, this is like the two-dimensional version of this kind of stuff that you do in, you know, one dimension. You know, you could have done something like this, right? And then something like this, that, right? So here, right, clearly these are equilibrium, right? And these are solutions that start at some other initial condition. Of course, what's the difference? The difference is in 1D, you have the luxury of drawing it with respect to time, okay? In 2D, right, you kind of throw away the time variable. You think of the time as implicit, right? And your equilibrium solution, right, are points. I mean, of course, right, it could have been just points too, right, like this, as in a phase line, right? And then for other initial conditions, right, for other initial conditions, you have other solution curve. So this is a solution curve corresponding to, let's say, this initial condition, and this is a solution curve corresponding to this initial condition, right? Exactly like you have initial condition here, you have this solution. Initial condition here, you have this solution, okay? Same kind of concept apply, meaning that different solutions corresponding to different initial condition should not cross, okay? Should not, but you know what I'm referring to, uniqueness, right? So somewhere along the future, we'll discuss, right? So basically we say this, solution curve, right, corresponding to different initial conditions do not cross, right? Same concept. If, right, uniqueness holds. Again, right, a topic of some very near future discussion that we'll talk about existence and uniqueness in higher dimension, right? Very, very similar to first to one dimension anyway. But so solution curve is like this. Of course, right, there's a kind of, right, the itching question, right, that everyone wants to ask is why does it look like this, right? Why a closed circle? Okay. So that actually, I have some partial answer to this, all right, which I'll tell you today. But of course, right, but by solution curve, all we mean is a attempt, right, to play around with sketching the solution, right, but with the time variable not being explicitly shown, okay, with only these dependent variables, right, plotting one against another, all right. So any questions so far? Oh, and also, right, I mean, there's a time here by the arrow. So you here you don't have to draw the arrow because it's always understood, right, that time flows to the right. But here, right, depends on the solution, right? It could have flown this way and it could have flown that way. So the time is actually indicated by the arrow direction. Now, so a partial answer to how to sketch the solution curve, right, is the direction field. That's not gonna satisfy people so much, but you know, we want to mention it anyway. And exactly the same, so this is right. So this is exactly the 2D version or multi-D version of slope field, right? So basically with slope field, right, what that gives us, if you remember, is a bunch of arrows, right? You've seen that enough in the lab. That allows you to basically indicate where your solution is following, okay? At that point, so you can just kind of connect the dots in a way. So direction field is the same way, right? Remember, for example, let's say, you know, dy1 dt, right, is, let's say, y1 times y2, all right, just to make it easy. Let's say dy2 over dt is like, I don't know, let's do y2 over y1, all right? Not that these are nice or anything, I'm just throwing some example out in terms of direction field. So direction field, right, will be, or sorry, I think they call it vector field. I don't know, vector field, direction field. So basically, right, you do y1, y2, right? And at some point of your choice, right, and as many points as you want, as you can, right, you plug in the values, right? So let's say at 1, 1, right, the coordinate 1, 1, right? Then your vector will be 1 and 1, right? Meaning the vector of the direction. So you would draw this kind of vector, right? And let's say further down the road, let's say, I don't know. Oh, I should have done y1, y2 like this, right? Down the road, let's say 10 and 1, right? Then the vector will be, that's silly, right? Because that's still what, because y1 is, oh no, that's fine. It's gonna be 10 and 1/10, right? And so 10 and 1/10 will be quite long, right? And quite shallow, right, in the y direction. And if you collect enough points, right, you collect enough arrows, then that will tell you how to draw the curve. Okay, so basically you can imagine that when you go in and try to do a direction field for the predator-prey system, the arrows will kind of circle around. Okay, the arrow will be kind of circling around. And so, of course, right, I mean, like here, I'm because of my choice, they're all positive, so that's why they all point right and point up. But of course, if you get a negative value, then that means it points left, right, for the first one. And if you got a negative value here, it means point down, right, for the second one, okay? But direction field, right, is a experimental slash, right, a MATLAB slash machine tool, right, for you to get a hold on these equations, okay? So the solution curve, okay? So maybe let's pause a little bit and let's take a look at some problems in the text, right, and then play around with that, and just to have an idea. Then there's a more precise way to get a hold on this solution curve, but that method is you know, it is not questionable, but it sometimes works, sometimes not, which I'll show you later. All right. So let's take a look at, right, this kind of thing, right? So exactly this is the direction field, right? So for example, let's take a look at 9, right? This is I think 9 in 2.1, if I'm not mistaken. Do I have it here? 2.2. All right. So let's see here. Sketch a number of different solution curves, right, on the phase plane. So phase plane, right? So I guess they call it phase plane as well. I don't know. You see, I think there's a solution curve like this, right? Where if you start above here, then you go down. But if you start below here, then you go up, for example, right? So here actually 0 looks like a sink, you know, and not that we say it to begin with, but that would be one solution curve, right? Like that. Anything else? I don't know. Feels like there's some kind of curving around, like, I don't know where this is going actually. It goes to 0, 2, I guess, right? And then this is going to 0, 2, maybe, right? And then this is going there, okay? But again, right, you see it's just connecting the dots. Yes, x plus 2y minus y, all right? For example, you see, I don't know, let's see at the point 2 and 2, right? So at 2 and 2, then y will be minus 2. So that's why it's point down. And then the right direction will be what? 2 plus 4 will be 6, right? That's why it looks like kind of shallow, because it kind of point more right than down, for example, right? So same thing here, right? Same thing here, except that I think here, this one is even more stable, like in the sense that everything kind of somehow swirl back to the zero solution, to a 0, 0 solution, you see? Wherever you are, you go back to there. Okay. Now, let's do one last one, right? And which is this. They want you to match, right, the system with the solution curve. All right. So let's look at A and see if anyone has any idea among these guys which one should be the right system. Let's do A and B, right? Correct. And the clue is, yeah, right? When x equals to 1 and minus 1, right, then there's no change in the x, right? It goes straight down. That means the x dt must be 0, right? When x equals to plus minus 1, pardon my writing, right? So there, right? Exactly because of this, the only thing that fits the bill is this, right? And yeah, you can throw in y equal to 0 is a sink, that kind of stuff. Are you sure the y equal to 0 is a sink? Oh, y equal to 0. I see this one. Yeah, right. But I'm not sure if I see that very well, right? But sure, right? Basically because of the minus y. Yeah. So everything, right, from top goes down, everything the bottom goes up. Sure, very good. Let's do one more, right? B. I think I agree with Daniel so far. I think I agree with Daniel so far. Let's wait for a couple more. What maybe I already put my put my support on that, so people might be swayed on that. Hat, what's hat? Hat is 6, is it? Or yeah. All right. What's the clue for you to say 8? Anyone? Yeah, the x equals to y line, right? X equals to y is a solution, for example. So, or basically, right? Actually, I was trying to think about that a little bit. X equals to y. I'm not sure what that implies though. But right, the solution should be x equals to y to begin with, right? That's part of it. Uh, so what I thought of, right? So again, x equals to y is clear, right? But I'm not sure what that means exactly. But it's kind of clear that 0, 0 is the equilibrium, right? To begin with. So if 0, 0 is equilibrium, you automatically throws out anything like this. Because, right, doesn't matter for now. But if it's an equilibrium, then these guys are out. That's all. Is that okay? And then the other containers, right? What do we have? What I have is I just noticed, I think someone said, maybe Daniel, right? If you look at it quadrant, right? This quadrant means x positive, y positive. But if it's x positive, y positive, it goes down and to the left. That must means that dx dt must be negative and dy dt negative in this quadrant. Okay, again, sorry, my writing. But if you glance at the rest, right, the rest of the candidate, if for example this is the case, and it will point up, right? Same thing, point up. So the only thing that points down and left is 8. So that's how I see it. That's how I see it. Okay. Any question on this? I mean, again, right, there are tons of ways. It's just basically you know how to read this graph and connect it to the system is the point. Okay, so actually I have one question. It kind of bugs me a little bit. I feel like there's some scale here that I'm missing out a little bit. Like if anyone knows, not that, you know, for example, I think William was saying, right, that here, for example, at the point 2, 2, right, it's going to be 6 here and minus 2 here. So in terms of drawing, it will be a large vector or something if I have to draw it. How could they draw all these vectors at the same size? So, and still capture the idea. Something is missing in terms of drawing this. I'm not seeing. You understand what I'm trying to say? I see it's more shallow, but is there some scaling that they're doing so that all these vectors have the same size? If I were, yeah, but if you normalize a vector, then are you losing out on something? So basically they scale, yeah, they scale it to length 1, right? Okay, so that's something that I think. But okay, so you get the direction, you keep the direction, but you miss the, do you miss it really? Yeah, actually, you know what, Daniel, I think, yes, lose, but not lose, because what's the point here, right? If you remember in Calc 3, direction is a unit vector. Unit vector is enough, right? If you remember, you only need the unit vector to point the direction. You don't need the magnitude. I mean, of course, like you said, I agree, it loses info, but as far as the direction field is concerned, right, we don't lose it. Okay, I got it. Exactly, yeah. So okay, I got it, right. So all these direction have the same length, right? But so you find it and you scale it. So for example, 6 and -2 will scale it down to, I don't know, right? 3 and -1 or whatever, right? And stuff like that. Okay, very good. No, Alborz, that's not true. Basically, magnitude, right? What we mean by magnitude is the length of the vector, right? For example, you see 6 and -2 here, while for example, close to here, right, say 0.1, whatever, you should get something really small, right? So if you really draw the magnitude, you see a tiny vector here and a humongous vector here. So what they do is they normalize everything to length 1 or something, right? But keep the direction. Yeah. Okay. So that's that. Okay. So direction field. But of course, right, again, after I showed you the direction field, right, it still feel a little bit like weird. Like, okay, you probably, if you try to do direction field of this, you might see that it circles around. You might believe it, right? But again, these directions are approximation. So how do you know it? Not that I have a solution here for you, but let's give you something like this. Analytical approach to derive, okay, solution curve, okay, and it's this. So let's look at the equation for the spring mass system, okay, as an example, and I'll show you later on with the other one. So sorry, all right. So let's do spring mass system. Okay, so spring mass system will be y double prime plus y is equal to 0. Let's say I just picked easy value, so I don't have to mess around with the arithmetic. All right. So if you check, right, then we got, let's say x1, right, is y1, x2 is y1 prime, and then I got, right, x2 prime plus x1 is equal to 0. Okay. So the system, if you will, sorry, what the heck did I'm saying? X1 is y, x2 is y prime, okay? So a system is something like this, right? And xy doesn't matter, but dx1 over dt, right, is equal to x2, right? Differentiate x1 gives you x2. And dx2 over dt, right, is going to be minus x1, right? That's the system. Okay. Now, solution curve. All right, solution curve. So first of all, I guess if you look at this and you try to, I don't know if you can eyeball it, but here's x1, right? Here's x2, okay? So the direction x2, right, is negative of x1. So for example, right, if you're over here, right, if you're over here, right, then x2 will be increasing, right? X2 will be dx2 over dt. How do I want to say this, right? But it doesn't. So it'll increase, but then it'll increase with a, okay, I don't know. So basically what I want to say is this. If you draw a direction field, you see that basically it's going to be a circle. Let me just say that for now. All right, it's going to be a circle. All right, it'll be a circle. So why does a circle make sense here? All right. First of all, the solution curve is circles. All right. Why does a circle make sense? Remember, what is it though? Right? It's a spring mass system. Right? It's a spring mass system where x1, right, is the position away from equilibrium. X2 is a velocity, okay? And so you see, I think the message, right, is something like, if you are the furthest away from equilibrium, right, then your velocity is the smallest. That's true, right, because it's kind of temporarily stops. And then you revert, right, the direction. And then when you are at equilibrium, that's when your velocity is the maximum. And the system, right, just go back and forth, okay? So that's actually believable. And again, right, you can do this with the slope field, plug it in and then sketch this, okay? I'm too clumsy to do that out. But the point I want to bring this up is this. I can show you exactly that the solution curve must be circles, okay? How? Because, right, I will do analytical approach. The how is this. The how is by a chain rule. I got dx2 over dx1, let's say, all right? What does this mean, right? Of course, this is the derivative of x2 with respect to x1. Will be, right, of course, dx2 over dt divided by dx1 over dt, which will be minus x1 over x2. Okay. Now, voila, what are you seeing, right? If you ignore this, which is just the explanation step, then this is a separable ODE. This is a separable ODE, right? Where x2, right, is viewed as a function of x1. Okay, can we solve it? You bet, right? So you got, let's say, something like dx2, x2 is minus x1 dx1, right? Integrate x2 square over 2, right, equals to minus x1 square over 2 plus c, x1 square, right, plus x2 square is equal to another c, right? Where c changes from this line to this line, but I don't care. C is determined by initial value. So exactly, right, is a circle. Okay. So the message, right, is that by this slick device, right, for autonomous system, if you're lucky, you may get an ODE that you can solve, right? Emphasis on may, because who knows what kind of system you get thrown on, right, for the right-hand side. The more complicated it is, right, the harder it is to solve the equation here, and the harder to track, right, what the solution curve is. But there's a hope in that sense that if you are the kind of people who are really interested in, right, precise solution, then this gives you one way to do it. Okay. By the way, this is discussed in N3, right, the supplementary notes on the department website. They give several other examples if you're interested. Any question here? So, but also, right, pay attention a little bit too. This solution curve is exactly a circle, but it doesn't tell us, right, what direction it moves in, for example. So for that, right, you have to go back to your original system and try to see, right, for example, so pick a point and see what direction it goes, and then you can draw, right, direction of the circle, for example, okay? Of course, solution curve does not have direction in it. Direction is given exactly by this. All right. So this is to show you it's not a cure-all approach. Let us go back to the prayer-to-pray system, all right? Now I'll just make an easy model where you have the RDT, right? It's gonna be, let me do this, 1 minus F times R. And let's say dF dt is uh, f times minus 1 plus r. Okay, so I make all the coefficient simple to do the calculation to show you, right? Needless to say, supposingly, right, the solution curve should be some kind of, right, and I insist it's not really circle, all right? It's a cycle, it's a cyclic solution, right? Emphasizing on the fact that the solution, the population, right, of the predator and prey kind of take a cyclical approach, right? If predator is high, then prey is low, but then if prey is too low, then also predator goes down, prey starts to pick up, that kind of stuff. But what our interest here is purely mathematical. How do we analyze this, right, in terms of this spirit, and see something more about the solution curve, right, beyond just like, say, doing direction field. So again, right, let's say if you think of f as a function of r, then you do the FDR, right, is, let's say here, right, f r minus 1 over r, right, 1 minus f, let's say. Okay. Separation of variable, right, again, not, right, you understand, not every right-hand side will be separable when you put it down here like this. If it's factor, right, maybe. But here, so we are lucky too that this is separable. So we got 1 minus f over f df, right, is r minus 1 over r dr. Integrate both sides. This gives us absolute value of f, natural log, minus f, right, is equal to r, right, and then minus natural log of r plus a constant. All right. So did I do it right? Yeah. So if you pull it together, right, you got something like natural log of f, right, and then times natural log of r, right? Sorry, plus, right? Which is, so adding natural log is like natural log of the product. So natural log of f times r is equal to r plus f plus a constant. If you care to exponentiate this stuff, you get fr is equal to e to r plus f c. Okay. Now, I stare at this for a little bit, and I kind of believe that it describes a cyclical curve. But I don't think, right, that is immediate. If anyone look at this, that they can say is gonna be a something like a cycle like this. If you see something, right, about how to translate or how to graph this curve on the FR curve to get to the picture, then I like to hear that, right? But there are several things that can help. For example, if you look at this, you see that basically, right, for every fixed value of R, there can only be two corresponding value of F. Second, R and F are symmetric. So whatever curve you have must be symmetric around the line F equals to R. So for that matter, right, a cycle solution seems to fit the bill. But all in all, right, this is not the circle that we're used to like this, where we say, oh, of course, that's a circle. All right. So sure, right, this is much better than nothing at all. But interpreting, right, even if you get to a solution, right, interpreting the curve or plotting the curve, right, it's not that, I don't know, immediate, as far as I know. Okay. Does anyone see how to look at this this curve and see that it's some kind of cycle? So I think the book, right? This is the plot on the book. Sorry. Yeah, like this, right? So it's really cyclic, right? And you see it's symmetric around the line f equals to r, right? And for every value of r or value of f, right, there's two values of r. So we see that from our analytical formula. But beyond that, right? And notice it's not really a circle shape anyway. So right, getting a circle shape is not like realistic here, of course. But so it's really a fun device to keep in mind, right? But like translating this, right? So I don't think the coefficient, I think, is quite simple. If you throw in some other coefficient, it's just a scale, I believe. The harder thing to decide is the effect of the exponential. The exponential has something of an effect of like, because if you throw away the exponential, if you just look at this, then that will be, of course, a hyperbola, right, like that. So the effect of the exponential is very interesting. With the exponential, right, it kind of pull that into some kind of cycle. I am not sure what you mean by the coefficients like the 2 and then something like that there. I believe those are simple to do by a rescale, I think. But I think the hardest effect to interpret is the exponential. Right. I thought about that a little bit. All I got is like, yeah, symmetric, two values, that kind of stuff. So, you have something like that there for it to go back. But beyond that, I don't know. But anyway, right, don't get too hung up on this. This is not a class on how to plot this kind of curve. Albors, I think you're mixing the concept. The exponential here is I'm not sure. So first of all, the exponential here is the effect on the graph, right? It's not on the slope to begin with, right? The slope is this. All right. So I don't know if that's what you're referring to, but sure, right? There's some effect of the exponential here on the actual graph, right? Like this. But I don't care for that to begin with. I'm asking, how is it that you see what I wrote, right? Something like RF is equal to E to R plus F, right? Something like that. I forgot. Why is this? Why is this a cycle? Right? I mean, like, basically all I know is to be able to say something is a cycle, you must be able to decompose into a cosine and a cosine here somehow. Like kind of do a parametrization, like calculus 3, right? R equal to some action of cosine. F is an action of cosine, sine, for example. But of course, right, this is hopeless because, relation between R and F is not exactly a circle. So maybe there are all the cyclic function out there that allow you to parameterize this, okay? It's really a fun thing to think about, really. But again, this is not the class for that. So I'll just stop here. My job is to tell you, right, that there are such things here, right, that you could get down to this step. But beyond that, right, don't get your hope up and say, I can graph that with any explicit solution. That's all I'm trying to say, right? So you can get your hand down to analytical solution of the solution curve. But beyond that, right, beyond that, it's your luck, okay? The harder the system. And by the way, right, predator prey is not that hard, right? So that's why direction field, is a very useful calculation tool. Let the machine do it, right? Just plot a curve and observe, rather than hoping for analytical solution like this, which is hard to interpret to begin with. That's my take on it. Any question? Okay. So now let's move on to 2.3. All right. So far we were discussing like kind of qualitative. So far, all right. Not exactly all, but 2.1 and 2.2 are more like qualitative analysis. All right. Qualitative analysis, right? So 2.3, the title is, what is it? Damped harmonic oscillator. That's the title. But in reality, right, what it's discussing is equation of the types, you know, a y double prime plus b y prime plus c y is equal to 0. And telling you how to solve it analytically, okay? So derive analytical solution for this. That's it. This second order linear ODE with constant coefficient. Okay. So again, right, the modeling, I hope is clear. First of all, this is Newton's second law, right? MA kind of stuff. This is a spring force. It should be on this side because it's the opposite of the, the movement, the position. This is the drag force, or the damping force, whatever that is, right? Is also the opposite side, right? Is proportional, right, and against the velocity, right? Against the velocity. So that's also minus, right? So A, B, C are understood to be positive, but it doesn't have to, all right? In the sense that the fact that A, B, C are positive plays a role in how the solution can be obtained in a certain ways. But I don't think we'll go that deep into modeling in this class. I mean, in terms of studying this system, if we do, I'll discuss more. I feel like the point of 2.3 is just to tell you how to derive the solution here. Okay, that's all. So I won't go. So in that sense, I don't assume that A, B, C have to be positive. So not exclusively spring mass system with damping coefficient. It's going to be just a generic math equation like this, right? It could model many things else because I don't require ABC to be positive. Okay, so mathematically, right? How do we approach this? So mathematically, how we approach this is by, so of course, right? We're looking for homogeneous solution. So we do this by making a guess on the form of the solution. Okay. Now, what guess would work? The obvious guess that would work is that basically, right, you look for a function whose derivative, right, and whose second derivative kind of goes back to its form, so that when you combine them, right, you get to get it to 0. For example, right, things that won't work will be something like t to the n, because if t to the n, then differentiate, you got t to the n minus 1, t to the n minus 2. There's no way you can combine these different powers to get 0, right? So the guess that would work is going to be y of t to be e to lambda t. All right. So then, of course, you complain a little bit and you say, what about cosine and sine? Okay, what about cosine and sine? In fact, you see, cosine and sine should be on your mind in the second order equation. All right. Why? Because we actually just show, right, that the spring mass system has behavior of a circle. So in fact, right, you see this almost so tempting to say that x1t is cosine t or something like that, and x2t is sine t, right? Because that's exactly one possible parameterization to give you the circle. Okay, so for that reason, right, why do we only consider solution of the form e to lambda t? The reason here is this, that we do allow lambda can be complex here, right? With the understanding that I think it's Euler's formula. Is it Euler or Euclid? I think Euler, right? Euclid is too old. By Euler formula. It is the same Euler, but not the Euler for your Euler method, but the Euler formula like this. E to the a plus ib is e to a, right? Forget that cosine b plus I sine b. Okay, like that. Yeah. So he's everywhere. He's in your numerical method. He's also here. Anyway, right? Yeah. All right. So this is Euler. Like that. So basically, right, the lambda here could be complex, and we could obtain something like that too. Okay. So cosine sine is not lost. Okay, by assuming this. Okay. So what do I do here? What do we do here? After we assume, right? After you guess this, then you plug into the equation and solve for lambda, and then interpret, okay, what your solution should be. So for that, let's do a concrete example. Let's do example number 1, problem number 1 in section 2.3. Okay, in their homework or in the exercise. So they say something like this: y double prime plus 7y prime plus 10y is equal to 0. Okay. So if you let y to be e to lambda t, right, then y prime is lambda e to lambda t, y double prime is lambda square e to lambda t. Plug in, right, you see that actually all the e to lambda t is going to hang around, right, and got canceled by 0. So if you plug in, what you get is lambda square plus 7 lambda plus 10 is equal to 0. So it's so routine that usually you don't even say this is your guess, you just jump to here right away. And this is called the characteristic equation. All right, the characteristic equation. So, and then that's it, right? So now you solve for lambda. You could do it by, quadratic formula if you want. But my experience is on these problems, especially coming from a textbook, they always have nice solutions. So look for factorization if you can. It can save your time a little bit. Here, factorization is clearly lambda plus 5, lambda plus 2 is equal to 0. So lambda equals to minus 2 and lambda equals to minus 5. Okay. Now, right, it's a fact of life that when we deal with second order equation, because you differentiate twice, you get lambda square, you always will get 2 solutions. Oh, good question, Lauren. If it's not 0, then remember it's a linear system. So you will treat it as what? You treat it as a homogeneous solution first, and then you will look for a particular guess of the non-homogeneous solution. Exactly the approach of 1.8. Okay, exactly. I'm repeating the story 1.8 here actually, but here the book only treats homogeneous equation, so I'm doing it for now. For non-homogeneous equation, of course not. So I'm saying 1.8. I'm not saying 1.9, right? Exactly 1.8. So Carl, because e to lambda t is going to hang out with everything, right? If you want, it's going to be this. It factor out. Yeah. So right, it's going to be always a quadratic equation. So you always get two solutions. Okay. Now, of course, those 2 solutions can be repeating. All right. Well, I'll talk about that soon. But in this case, right, then you got y1 is e to minus 2t, y2 is e to minus 5t. Okay? These are two solutions, and your general solution will be c1 e to minus 2t plus c2 e to minus 5t. Now, if we are looking for homogeneous, we can throw an h in here if you want. But here, because this is the only equation we look, don't care for that. So that's the solution. And the reason why we combine this like this is by the linearity principle. And that's your answer. Any question on this? So okay, right? So before I continue, right, and talk about the different cases that can happen, let's revisit, you know, the first order case. All right. I mean, suppose you have something like this: 2y prime plus 3y is, let's say, e to t. All right. Again, right, you have seen this enough times. Of course, you can use integrating factor, all the kind of good stuff. But if you just focus on, let's say, right, homogeneous equation, and I know, right, good practice tells you to divide by 2, that kind of thing. But doesn't matter in the sense of like what we're looking for here. Because if you look for, right, y equals to e to lambda t, then the characteristic equation will be 2 lambda plus 3 is equal to 0. So lambda is minus 3/2, and exactly y of t is yh, right, is c e to minus 3/2 t. Right. So actually, this works in the one-dimensional case too, except at that time we have too many things to work out that way. So I was telling you to use separation of variable, whatever you want. But right, this method also works. All right. So let's tell you quickly. All right, different cases in for a second order equation. Cases, okay, for lambda. You can have first two real roots, lambda 1, lambda 2, like this. Then your equation will be c1 e to lambda 1t plus c2 e to lambda 2t. All right. Second case is repeating roots. You only have lambda 1 equals to lambda 2, and let's call that lambda. Then your solution will be c1 e to lambda t, right? But you cannot repeat this, right? Because then you get the same solution. So the second solution will be t e to lambda t, all right? The same exact principle as I talked about when you get coincidence, right? In ODE, when you have like something coincide, to get out of it, usually the routine is multiply by t and try your luck. Here it works. All right, so this is the second solution. Third case, complex roots. And let's say lambda, right, is equal to, let me call this, I don't know, r plus minus, right, I don't know, ic, right? No, let me call it a plus minus ib. And by the way, right, it will be of this form because it will be of this form, right, because of the quadratic formula, right, minus b plus minus square root of something. The square root will give you the I term, and then this is a minus b over 2. So anyway, right here, the solution will be e to the at c1 cosine of bt plus c2 sine of bt. All right. So I just kind of blast through, right, these two cases. I think this is obvious from what we just discussed. These two cases, all right, I'll elaborate them on a little bit more on Friday, okay? But I think intuitively they're quite clear on why they take on that form, for example. So you can go ahead and use them if you want, right, to solve your problems, but we'll discuss a little bit more on them on Friday. Okay, any question? No, you don't want I. You do not want I. That's the key. Yes, that's the beauty of it. You don't want I here. Why not? I mean, you could have I potentially mathematically, but remember, what is this? This is a spring mass system. The coordinate, right? The position from the balance is a real solution. If you introduce I in here, right, at least to the untrained eye, that looks weird because your solution should be real, right? So there is a way to get rid of it and not to have the I in there at all. Of course, the answer is very simple because you hide the complex coordinates in here. So you kind of choose C1, C2 that cancel out the I. But we'll talk about that on Friday. Yeah. Yeah, thank you. Okay, yeah, see you on, wait, is it Friday? No, Thursday, sorry. Why do I keep saying Friday? I messed up my schedule. Thursday. All right, I'll see you on Thursday. Yeah, you want to talk in public or in private? Okay, go for it. What is it that you want? Let me stop recording, all right? I think this is irrelevant.